x is equal to 1 over 3 allows it to go to 0. Now, as I increase this without bound, as I increase x without bound, this whole term also grows without bound. And so the square root also grows without bound. Makes sense? So this will go from 0 to infinity in this case. Is it clear? If so, let's discuss the next problem. I want you to prove that this limit exists by delta epsilon. I'll give you 5 minutes. Don't supply the whole proof. Just tell me what epsilon would be. Sorry, what delta would be, because you base delta on the choice of epsilon. Yeah, good question. So someone is asking whether we need to prove or demonstrate the process how we got our desired L value or the limit value. The solution would be no, not really. You can probably guess, have a reasonable guess about what the value would be. Okay, did anyone find what the limit would be? delta is equal to 16 epsilon, or okay, let's see. It should be close, or it should be that value. No, I don't think it would be the square root. Hold on. Okay, what's the limit first? What's the limit you guys are guessing? All right, so the limit is 0. Let's try proving it. So let L is equal to 0 as a guess. I want to show for all epsilon greater than 0, there exists delta greater than 0 such that this will be x squared plus y squared is less than delta. This should imply that y to the 4x minus 2x to the 4 plus 16 y to the 4. This would be less than epsilon. This is the definition of delta at epsilon. Now, how do we bound this? Let's try. We first expand this term to be 16x to the 4 plus 16y to the 4. We can say this is equal to, we can separate the terms with the absolute value, x to the 4 plus 16y to the 4. Now, since x to the 4 is greater than or equal to 0, we can say y to the 4 is less than or equal to x to the 4 plus y to the 4, right? We can do this. So this will be less than or equal to x to the 4 plus y to the 4 over 16x to the 4 plus 16y to the 4 times its absolute value of x. Factor the 16 out and cancel. You will end up with root x over 16. Now, how do I turn square root of x into something of this form? The square root of x is just the absolute value of x is just the square root of x squared, right? And we realized that the square root of x squared is less than or equal to the square root of x squared plus y squared. Again, since this is greater than or equal to 0, and the square root is a strictly increasing function. So this is equal to the square root of x squared over 16, which is less than or equal to the square root of x squared plus y squared over 16. Now, do we have an upper bound for the square root of x squared plus y squared by any chance? Yes, it will be delta. So it will be less than delta over 16, and that's what we want to pick for our epsilon. So yes, delta will be 16 epsilon. Someone in chat has pointed out. Now, this is the aside. How you'd go over your proof would be to say, after you do this aside, you say that delta is equal to 16 epsilon, and suppose square root of x squared plus y squared is less than delta, and you largely do the same exact steps over again. So you start with this. You say the square root of y to the 4x over 16x to the 4 plus 16y to the 4. And you end up doing this exact bounds again. Just to make the proof more formal, you have to let epsilon be 16 delta, because that's the choice you want to make, and you want to show that this choice works. How do you show it works? We just showed it, but you kind of have to show it again. All right. Does this proof make sense? If that's the case, we can move on to the next proof. I'm giving you a piecewise function. F of xy is equal to h of c. This is some arbitrary polynomial times x squared, polynomial of c. It's independent of variables. X squared over x squared plus y squared whenever xy does not equal to the origin, or 0 whenever xy is equal to 0, 0. I want you to show that the set of values C belongs to R, where f of x is continuous at 0, 0, h of h is a non-zero polynomial. So h does not equal to 0. It's not the x-axis. It's not a constant, because a constant is also technically a polynomial. If h is a non-zero polynomial of degree, say 4, how many zeros does it have? Do you have an upper bound on the number of zeros? No, it actually has at most 4 zeros. So it has at most 4 zeros. By fundamental theorem of algebra. Now let's examine this function. Let's say h of c is equal to some constant a, right? So suppose I have ax squared over x squared plus y squared. We don't make any assumptions about if it's positive or not. H of c is not necessarily degree 4 right now. I'm just giving you an example, right? I'll explain why I said it's non-zero later on. So this is x squared over x squared plus y squared. It's the same definition. And 0 when xy is equal to 0, 0. We first, for it to be continuous, limit as xy approaches 0, 0 of ax squared over x squared plus y squared has to be 0 for f to be continuous, right? But if a is not equal to 0, I can pick two paths. Let y is equal to x, then ax squared over x squared plus x squared will be equal to a over 2, right? That's one path. The other path would be, say, 2x. The limit as x and y goes to 0, 0. Then the limit will be the limit as x goes to 0 of, so this should be x approaches 0 of x squared plus this time x squared plus 2x whole squared, then ax squared over 5x squared, which is a over 5. Whenever a is non-zero, are these two the same? No. So if A is non-zero, limit does not exist. So f is not continuous at 0, 0. Thus, A has to be 0. Now suppose I replace A with h of c non-zero polynomial. What values of h and c, what values of h of c make this continuous? Is it h of c equal to 1? H of c is equal to 0? It's not no values. We have some values. So the only values where f is continuous would be those where h of c is equal to 0. But if h of c is a non-zero polynomial, how many roots do I have? Yes, exactly. By fundamental theorem of algebra, I have at most as many zeros as degree of h, which is finite. Thus, so these are the choices for C where f of x is continuous and h is a non-zero polynomial. If this is, since I found out that the number of roots of h are finite, then I proved that the size of S is also finite. This is what absolute the coordinate of S less than infinity mean. I'm saying the size of S is finite. Does this make sense? Any questions? Yeah, sure. Okay, so for the last part, h of c is independent of x and y. Someone is asking me about the fundamental theorem of algebra. That's what the fundamental theorem of algebra basically says. That's the claim we're making, essentially. you want to be really accurate, the fundamental theorem of algebra says each polynomial that's non-zero has at least one complex root, right? So say h of x is equal to x squared plus x plus 1. This has at least one complex root. I don't want to get into complex factorization stuff. I'm sorry, what do you mean by wxxx have zeros? What do you mean by a question? I don't get it. Wouldn't a positive n degree polynomial have at most n minus 1 roots? No, surely not. Consider this polynomial. This polynomial is degree 2, and it has 2 roots. It's not n minus 1 roots for sure. Yes, at most. We just want to show that the number of roots is finite. By the way, does this claim hold for an arbitrary function? No, these are zeros of h. So h is some, instead of having some constant, I'm allowing h to vary over c, some other variable. It's not related to the function itself. Got it? So I want this polynomial term to vanish. I mean, we don't care if n is positive or negative. If it's positive, it's negative. Any non-zero value h takes would ruin the function because the function would have no limit at this point. We showed that if you substitute a for any constant a that's non-zero, the function has no roots. Sorry, the function has no limit at 0, 0. If h was trigonometric, would it still be finite? No, actually, not necessarily, because it periodically visits 0. So if you replace this with, say, something like sine of c, yes, exactly. And you need not have countable roots either. So actually that was going to be a true and false question. Whether they will be countable. You can have some wild function that just zips around here and takes on a 0 at all the values of 0 and 1. Something like this, the floor function. Do you recognize the floor function? Yeah, non-zero, not non-negative. So if x is between these values, so let's say this is f of x is equal to this. This is the floor function. The definition of the floor function is it rounds it to the nearest integer from the bottom. So if it's an integer, it fixes it. If it's less than some integer, it rounds it off to the nearest integer. So it essentially subtracts so it's something like 4.9 something. It goes to -5. It goes to the next lowest integer you can find. In this case, so 0, 0.1, 0. Blah, blah, blah. All values between 0 and 1 are solutions to this. So in this case, if I replace h with f, this wouldn't be finite set anymore. This wouldn't even be a countable set. By countable, I mean let S be a set. There exists an f such that f maps the naturals to S surjectively, or actually bijectively, if I want to be more exact. Okay, this is the definition of countable. By countably infinite. I won't get into too many details if you don't know this, but this set between x greater than or equal to 0, less than 1, this is not countable at all. So it's even worse than just infinite. But regardless, you guys understand this one? So having a function as well behaved as polynomials is actually necessary to make such a claim. All right, if this is clear, let's move on to the next question. Now, how would I write this in polar form? Well, it should be simple. This one is the inner product. So x comma a would be just x times 1 plus y times 1, which is x plus y. Since a is equal to 1, 1, and x y is equal to xy. And again, this is equal to the square root of x squared plus y squared. Now, how do I do a polar substitution? R is equal to the square root of x squared plus y squared. And x is equal to r cosine theta, y is equal to r sine theta, so long as theta is between 0 and 2 pi. And we usually want r to be positive, although r to be non-negative, although r being negative does have some meaning. You just have to do a reflection. So we rewrite this as e to the x plus y over the square root of x squared plus y squared, which would be e to the r sine theta. Sorry, this one will be cosine. R cosine theta plus r sine theta over r, which is e to the cos theta plus sine theta. So from this point on, it will be f of r theta, and it's actually independent of r this time. Do the substitutions make sense? If the substitutions make sense, we can move on to the next question. We're not talking about the limit for this one. In polar form, if it's dependent on theta, then the limit does not exist. A limit where exactly? The limit as what approaches what? If you're trying to approach 0, 0, then you're fixing some theta and you're allowing r to move to 0. But if you're fixing some theta, this will have a different value. Like the limit as r approaches 0 would be this. But it would depend on what value you choose for theta. This is the exact same as I showed before as approaching on a line. Y is equal to x, y is equal to 2x, y is equal to 5x, and so on. You're just playing with the theta and you're approaching along the line. So there are two ways in approaching this. if I do a substitution with xy, end up with r theta, say r theta, I end up with this expression. Say even not expression, I ended up with something like this. Sorry, not this. I ended up with this. I want r to go to 0, right? So this would be the limit as r theta approaches 0. Limit as r approaches 0. I cannot, letting theta approaches 0 doesn't accomplish much here in this case. You know, since x is equal to r sine theta and y is equal to r cos theta, if I keep r non-zero and just play with the theta, definitely one of them will be non-zero. So that doesn't help us. So if I do something like this, cosine theta plus sine theta, that limit will be cosine theta and sine theta. That limit would depend on which value theta takes, right? So for one theta, that limit would be something, and for another theta, that would be a different limit. What does this correspond to? Fixing theta and playing with r. This corresponds to fixing a straight line, because a straight line has the same angle throughout with the origin, and then you're just proceeding along the line itself. So if you do something like this, if you do some substitution of this form and you find out there's no limit, it's actually the exact same technique. You could have done almost the exact same thing by, say, letting y equal to ax, letting y is equal to bx. All right, so let's go to the next question. I'll give you 3 minutes. It's not a hard question. I just want you to give me the justification for where this is continuous. So you start by finding the domain and then say why it's continuous on these parts of the domain. All right, so what's the domain of this function first? Yes, when does that happen? When does x squared plus y squared not equal to 0? Yes, exactly. So we recall that sine x has no restrictions on domain, or has domain r squared, domain r. 1 over x squared plus y squared has domain r squared minus the point 0, 0. So what would be the domain of the composition? The domain would be just r squared minus 0, 0. How about continuity? Where is this function continuous and why? Yes, it's continuous on its domain, but how would it be continuous? How would we justify it's continuous on its domain? It's a rational function. Okay, yeah, that should work. So x squared plus y squared is polynomial. That's one way you can do it. 1 over x squared plus y squared. These two continuous. So ratio is continuous as long as the bottom is not 0. So continuous on r squared minus 0, 0. Now we consider sine x continuous on r squared, on r. We know that sine x is continuous on domain. By composition, if it's continuous at, so it's continuous at the inner function, and the outer function is continuous at the evaluation of that point at the inner function, then they're both continuous. You can see this by considering the limit laws for decomposition. So by composition, sine 1 over x squared plus y squared is continuous on r squared minus 0, 0, which is its domain. So we want you to justify all of that when you're saying something is continuous. Don't just say randomly is continuous. Yes, sine x is continuous in its domain. That's one thing you can say. The other thing you can say, rational functions are continuous wherever the top and the bottom are continuous and the bottom is non-zero. That's one thing you can say. You said just state sine x is continuous on its domain. I'd rather not, honestly. But it helps you. Just say the composition of continuous function is continuous. All right, so let's move on to question 10. I'm giving you the mapping xy to x squared y, y squared e to the x. This is an r squared to r squared mapping. And I want you to argue that df exists and compute it. How would the total derivative look like? So let's call this F1 and call this F2. 2 by 2 matrix, yes. What will be the first element here? partial of what with respect to x? f1 or f2? Yes. How about the second element? df1 dy, and the rest follows. df2 dy. The computation will be trivial here in this case. You just take this with respect to x, with respect to y. You've done this a lot. Now, how do I argue the derivative exists, the total derivative exists? You can do it using the limit, obviously, but that wouldn't be too good because it would take you a lot of time. You're given some major theorems. So what I would suggest would be to use the major theorems to justify these are the total derivative exists here. Which major theorem do you use? And which hypotheses do you have to check? Any suggestions? You can argue by definition, yes, but it will be somewhat painful to argue by definition. But how do you argue by both exist and continuous and AB? What exist? I just want to make sure you get what you're saying. Partials. Yes. So the one mentioned in the sheet, in the extra pages or the extra readings is z is equal to fxy. You say, oh, dz1, dz dx, dz dy exist and continuous. Actually, hold on. Does it say continuous? So it says continuous at AB. We have to check something else. Yes, they have to exist near AB. And they have to be continuous at AB. Now, how do you check they exist and they are continuous? Well, in this case, since this is a polynomial function or an exponential function, no matter how many times you keep taking derivatives, the derivatives will keep existing and will equal to the derivative. Will keep existing everywhere on their domain, basically. Sorry, what do you mean by limit is equal to f of AB? Yes, you can do this, but I want you to stay away from the definition for this problem specifically because it would consume a lot of time from you in the midterm, for example. The idea here is basically to compute the partials and then argue that they satisfy the conditions required. So the partials would be sum or product of exponential functions and polynomials, right? So in this case, the partials are defined on R2. So if they're defined on R2, they exist everywhere. And now you just have to argue, since they exist everywhere, they exist in some neighborhood of your desired point. By the way, we normally talk about df at some point 1,1 or some point AB. Yes. So in this case, you're given 4 partials you have to check. All 4 of these partials have to exist. in a neighborhood around x and y. And also, all of these partials have to be continuous at AB. So they have to exist at all x, y around. So say this is the neighborhood and this is AB. So they have to exist at shaded region, and they have to be continuous at AB. Does that make sense? Okay, if that makes sense, we can move on to the next problem. But the last step of this problem would be to say we can apply this to any arbitrary point. What if it's 3 variable? Well, if it's R3 to R2, you would have 3 partials here in the first one and 3 partials in the second row. So you have to check for 6 partials. You have to check all partials you could come up with. You get what I'm saying? So for any Rn to Rm, you have n times m partials to check. Does continuous of function apply defined at point and limit exists? Yes, continuity implies that the function is defined and it's equal to its limit. So yes, that's right. For 3 variable, how do we state continuity? Well, if it's Rn to R, it's the same definition. You have xy minus AB, the difference between the norm of the difference between these two. So this time I'll have it be a vector, x minus a. A is the one you're trying to approach. X is your vector of say x1, x2, blah, 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 xn. This should be less than delta. This should imply that the function is minus the limit is less than epsilon. Just like usual. Someone is asking, if we differentiate all of them and they are the same, what do you mean they are the same? So this is something you proved before. For polynomials, their derivative is just taking the derivative normally. The derivative exists everywhere. We don't ask you to prove that the function is continuous again. Not all 4 expressions should have the same partial derivative, but if it's the same, if you differentiate, say, for example, d of f1 with respect to x, this would be 2xy. Yes, if you get that this is 2xy, regardless of your choice of x and y, it will actually be continuous in this case. Because it's a polynomial. Got it? Okay, any other questions? Okay, let's move on to the last question. The last written question, at least. So I want to show that the partial derivatives with respect to x and the partial derivatives with respect to y exist and equal 0, but the function is not differentiable at 0, 0. So let's write this down. Let's write the definitions down. So partial x with respect to 0, 0 is equal to the limit as h approaches 0 of f of x plus h 0 minus f of, sorry, not x plus h, x is 0. So limit of f of h 0, so f of 0, 0 over h. Now, how do we compute this? F of 0, 0, by the definition of the function, is just 0, right? Because y is 0. And the same here, right? So by definition, this would be the limit as h approaches 0 of 0 over h, or the limit as h approaches 0 of 0, which is 0. So the partial derivative with respect to x is equal to 0. Let's try the partial derivative with respect to y. The definition would be limit as h approaches 0 of f of 0h minus f of 0 over h this time, while the second point is 0, right? Second point is 0. So the first point would be 0 over h, right? Because as h approaches 0, we're assuming h is non-zero. So we'll have to use this definition of the function instead, x over y. So we have 0 over h minus 0 over h, which is equal to limit as h approaches 0 of 0 over h, or 0 again. This is by definition. Now let's examine df at 0. This should be the limit as h approaches 0 of. Now we write this as follows. Actually, it wouldn't be h this time. Let's write xy approaches 0, right? So this would be f of xy minus the following expression. This is, by the way, for the single variable, this is the exact same, not single variable, I mean real valued functions, r and to r. This is the exact same expression as the one you find for the tangent. So this would be f of 0 plus partial f partial x at 0 times x minus 0 plus partial f partial y at 0 y minus 0 over x minus y. Contrapositive major theorem 1. Okay, major theorem 1, it says if f is continuous, if f is differentiable, then f is continuous at AB. Good question. Let's see. How do you suggest we use the contrapositive? F is not continuous at 0. All right. Which path would you pick? X is equal to y. Yes, you can pick x is equal to y. No, don't pick x is equal to 0. You get that the limit is 0. If you try x is equal to y in the first glance, you would get that the limit is 1, whereas the function is 0. You don't even need to test if the limit exists. If the limit as just a single path is 1, and the function is supposed to be 0 at that point, then we don't have the thing. We don't have. It's not continuous at that point. That's one way. So option 1. Oh, by the way, you still have to do these two, regardless. This is the third one, and I'm deliberately using it to show you the definition of the limit, because some of you may not have seen the definition yet and have a tutorial at, say, Friday or something. And the test is Saturday, so I wanted you to see it before then, to see the definition of the derivative, the total derivative. So option 1, show it's not continuous at 0. Major theorem 1, contrapositive. Option 2 is definition. Choose path y is equal to x. Here, recall that the derivative is 0. We just found it. The derivative is 0. The derivative is 0. At the point, the function evaluation at 0 is 0. So this reduces to limit as xy approaches 0, 0 of f of xy over x minus y, which is the limit as xy approaches 0, 0 of, since y is non-zero, we pick this definition. If you can do it without resorting to the definition, then you are free to do so. But when the function is usually piecewise, I suggest that you at least use the definition or check that, or do a sanity check that your differentiation normally without using the definition works. I'm not going to plug 0 in the den. This is just a regular limit. It's not 0, 0. Actually, this is even worse because I'm sorry? Yeah, you cannot plug in 0 in the denominator, but we don't want to plug in 0 in the denominator in the first place. When you compute partials, yes, yes. See, that's why we said the definition should work better in these cases. Now, if you pick f of xy, the thing you resolve f of xy to, it's not even x over y. You have to pick a path first. So if you say pick y is equal to x, then at all non-zero points, it will be limit as x approaches 0 of 1. So it will be x over y, which is x over x. So it will be 1 over square root of, sorry, this is not x minus y. This should be x is equal to xy. This should be the difference between x and the other point, which is 0, 0. So the difference just reduces to this point. So again, as you expand it, it will become x squared plus y squared, which is the limit as x approaches 0 of 1 over 2x squared, which, surprise, surprise, it diverges in the first place. So there is no limit. So if you pick this path, y is equal to x, you're allowed to do the substitution y over x, right? You're allowed to do this substitution. So you're allowed to do this substitution over x, which is x over x will end up, sorry, this is x over y. Regardless, it will be x over y. You substitute x, y is equal to x, it will end up being 1. You end up substituting in this. Could you go over how we would do it with contra of major theorem 1? Yes, that's actually the easier way. I'm just trying to show you the definition and how it works. Okay, so in this case, we ended up attempting to find the limit in a path for the derivative. We picked a convenient path so that f of xy is defined. You can use this definition. And after picking this, we ended up with this expression, which diverges to infinity. So not differentiable. The other way would be to show major theorem 1 states differentiable implies continuous. Where differentiable, this is D, not the partials. This is the actual D. So D must exist. This implies continuity. So if you show it's not continuous, this is the same as showing it's not differentiable by contrapositive. And in fact, you could approach, if you approach it at the line y is equal to x, the limit will be 1, right? but 1 does not equal to 0. So even if the limit existed in the best cases, it would still be not continuous. So this is why by major theorem 1, we say it's not continuous. Does that make sense? It's just, okay, how would you compute the limit? If I pick y is equal to x, then y is equal to 0 if and only if x is equal to 0. But since we are approaching 0, 0. We are not at 0, 0. So all points that are not 0, 0 will admit this function definition. You see why? Because y is not 0 at these points. Do you understand this? Does this problem make sense? So for the first two, I suggest you use the definition. For the last one, for the part where you prove it's not differentiable, you can use the definition. At least you saw the definition, but major theorem 1 works better in this case. All right, so let's do some true and false. Let me launch the poll. True or false, and why? So it seems 2/3 of you have said, oh, it's changing actually. So almost half of you said true and almost half of you said false. Can each side post y true or y false? So why is it true for those who said true? Oh, this is the problem. Yes, exactly. So if the domain is R2 that says nothing about its continuity, I can make a function that's discontinuous everywhere, but it's defined everywhere. Yes, you can make a piecewise defined function, a terrible one, where it's continuous nowhere, or it's discontinuous at some points. So the answer would be false. Just take, say, xy, then f of xy will be equal to xy if xy does not equal to negative 1, 1, and 5 if xy is equal to negative 1, 1. If this were continuous, then this would be negative 1, but it's 5, so it's not continuous. So since it's not continuous, the limit does not equal the point, the evaluation of the point. Do you get this? So it's false. Let's try another question. We solved this one. Let's do this. Okay, seems like the majority of you have chosen false. How would you show it? Yes, you need xy and fy to be continuous, and most of all, oh, actually should make this, though not necessarily. Though not necessarily at AB. So let's take a function like say 1 over x squared plus y squared. If you take the partial derivative, it will actually end up being differentiable everywhere besides 0, 0, right? But the differentials don't even exist at 0, 0 because the function doesn't even exist at 0, 0 in the first place. Right? So how will it be continuous if it's not differentiable? Sorry, how will it be differentiable if the point doesn't even exist at 0, 0? So this is why false. So existence in some surrounding area of A and B. So when you say exist near AB, so neighborhood is a formal term. Let's say near. If I say it exists near AB, I'm not saying it necessarily exists at AB. Maybe it would help if you want to clarify this term. But in this case, I'm explicitly saying it doesn't need to be defined at AB. It doesn't need to be differentiable. The partials don't have to exist at A and B. So this would be false because it's not continuous because it doesn't exist. And by major theorem 1, not continuity implies not differentiability. Does that make sense? Now, our final question. Read this one carefully. All right, we're kind of running late, so let's end this poll. So for those who said it's true, why is it true? And for those who said it's false, why is it false? Any justification? Okay, so contrapositive seems to make sense. Okay. Okay, so one way you can do it, this is an implication, right? Yes, yes. False implies false. False implies anything is true. Biological laws. So this implies this is true. And this implies false is also true. Why is sine square x squared plus y squared having a limit? So x sine x squared plus y squared, does it have a limit as x and y go to infinity? The limit doesn't exist. As r increases, it keeps oscillating. Yes, it keeps oscillating between 0 and 1. It doesn't get a specific limit. So this is actually false. And the whole thing is vacuously true. Right? And with that, we conclude our seminar. Any final remarks? Any questions? Well, if there are no more questions, that will be the end of our seminar. Thank you very much for attending and good luck on your midterm on Saturday. See you there. That's all.